Are the people from group B here? Can they just tell me? Yeah, if they want to tell me something, the people from group B, because I know that you guys went through a little bit of a disappointing challenge for challenge 2. So, anybody from group B is here?
Yep.
Okay, they won't just tell me something. Just tell me that you haven't lost faith in the class organization, in the class pedagogy, and that's it. Yeah, see what you want to tell.
Okay, so Azel, can you?
Oh, okay.
Yep.
You want to present something else that happened since the last class? Is there something else? Okay.
As I said in the last class, nobody responded to me, but when I said that, some people responded to me, actually. So they said that they, and most of the people have done their parts.
Oh, really? Okay, very good. That's a good sign.
But still, our second leader is just a superior. So we have 4 members now. And
okay. Just tell me what you want to tell me. I'm just happy that you're the happy ending eventually. Yeah, go ahead. Tell me everything.
Yep.
Tell me.
Okay, Zel, you can say your words.
So can we start now?
Of course. Go ahead.
Okay. So this is Group B, and this is our presentation of Challenge 2, Poisson Regression and Count Modeling. And so far, we have only 4 affected group members that did that, and the other 2 I grayed out. They pretty much dropped from this challenge. And this is our contents of presentation here. And in this challenge, we'll be exploring the red wine quality dataset and try to see the regressions of those predictors. And then we'll try to see why ordinary method of linear regression will not work well on this dataset. And instead, we'll try to use various Poisson models to find a better regression of it. So first, after importing the dataset, we can see that in this dataset, there are no missing values, so it's pretty easy to work with. And we can see the response variable quality consists of discrete integers, which will be the key part later. And
let me just comment. I mean, it's a little bit of an overkill because the highest grade is 6, so they could also choose int 8, right? So they go int 64. They could choose int 8, but of course, they're not concerned with the memory occupation here. Go ahead.
Okay. So at first glance, we can see that the response variable is discrete, and you can see the shape is a little bit right skewed there, like the 5 and 3, this shape here. And here are the 2 key predictors we suspect to have some sort of impact here, like the alcohol content and sulfate, because you can directly test the intensity of the wine by its alcohol content. And about sulfate, although you can't really taste the sulfate, it helps preserve the flavor and aroma of the wine. So we think it might also have some effect on it.
Okay.
And after that, we also quickly generated a heat map of the coefficients. Correlation coefficients. And we saw that there are a few pairs of predictors that have a little bit high correlation coefficient. So if we do linear regression, we might have some issues with linearity there, but this wouldn't be the biggest problem, however, as we will see later.
Okay.
Until the linear regression baseline part.
Hi, sorry, can you reload the slide for me? Yeah, I've updated something. Okay, thank you. So here I'll be presenting the linear regression baseline part, and the right is a linear regression equation. So next slide. So here's our code to fit the linear regression model with OLS, and the left is the training summary. Okay, next slide. So here the result shows that the MSE is high and the R-squared score is very low. So this shows that this R-squared score shows that it's not a good prediction since it's not close to 1. So since the quality category is the response variable is qualitative, the linear regression cannot handle this very well. So it will give some nonsense values.
I wouldn't say qualitative, right? I would say integer. A positive, yeah, I would say integer. I would say positive integers. Because if you say qualitative, somebody might think categorical, right? So I would just say, yeah, I would just say positive will find support. Go ahead.
So the
yeah,
minimum.
let me just start, because today we're going to see the qualitative case. So today we're going to do logistic regression, which fits more on this qualitative type of prediction. Go ahead.
So the model didn't predict negative values. I think this is because the actual quality values ranges from 3 to 8. So yeah, it wouldn't be reasonable for the model to predict that's negative value. Yeah. So next time. So here you can see the variance didn't really show a lot of how do you pronounce it? Heteroscedastic. So it didn't really increase. The variance didn't really increase with the mean. There's only a slight indication this happens. Yeah. Okay, next slide. So from the residual versus fitted value plot, you can show that it does deviate from normality, and it forms a distinct diagonal band, rather than normally scattered around 0. So this is because the quality value is discrete integer, so it's not normality.
Okay, so now I'm going to talk about the Poisson regression fundamentals. So in Poisson regressions, our goal is to model the probabilities of observing the count values in the data. So like linear regression, it minimizes the square errors, but now here we maximize the likelihood of the data under the Poisson distribution. So for each observation, the probability of seeing y given the model is the first formula. So if we multiply all these probabilities together, we get the likelihood. But multiplying many probabilities is really hard. It's numerically unstable. So we take the log likelihood instead as the second formula. So taking logs can turn the products into sums, so it's easier to compute and easier to optimize. Then we have to do the gradients. So to find the best parameters beta, we want to choose the values that maximize the log likelihood. So we can just solve a closed form equations like linear regression. Because the Poisson models use the exponential link, so instead we take the gradient, the log likelihood, which is the third formula.
Okay.
Okay, next slide. Okay, so here I use Adam because I learned this from another class. So Adam is short for adaptive moment estimation. So it is basically a smarter version of normal gradient descent. So the idea is very simple. When we update model parameters, instead of using just the current gradients, Adams keeps two running averages. So the first one is a moving average of past gradients, acts like a momentum, which is the first formula. So number two is a moving average of past squared gradients, which tracks gradients magnitudes, which is the second formula. So these two pieces of information helps the optimizer decide which direction to move and how big a step to take. So then we update the parameters using the formula 3. So here alpha is the learning rate, while epsilon is a small number that prevents division by 0. So what can we see from this formula? So this means that if gradients are consistently pointing in one direction, then Adam accelerates. But if gradients are large or unstable, atoms take smaller steps. So if gradients are very tiny, Adam can still make progress. Okay, next. So I was thinking that I asked some of my friends who will also take this course on how to do part 3 because I spent a long time doing Adam. And I found that most people use a third-party statistic package, which is stats models, and which relies on the classical second-order optimization methods. So it uses a method which is called Newton's method. So Newton's method is an iterative optimization technique that uses both the slope and the curvature, which is really hard. So in gradient descent, we move the directions of the gradients. That means we only use first-order information. But now Newton's method goes further. Use the second derivative, or the Hessian in multivariable problems.
Hessian. Yes, the pronunciation is Hessian. Doesn't matter. Just for you. Hessian.
Yep. So you can see for maximizing beta, we can get this formula where f is the gradients and the h is the Hessian, which is a second derivatives matrix. So if it's a minimization problem instead, so we put maybe a minus in front. Okay, so because this is really hard, so I think I did not really quite know what it's doing, but the intuition maybe is that the gradient tells you the direction to move and the Hessian tells you how curved the surface is. So instead of taking small steps like gradient descent, Newton's method just can jump closer to the optimum by estimates where the function peaks or bottoms out.
Let me add something here, right? So another way to see it is that gradient descent is as if you take a function, you take the linear approximation of the function through Taylor expansion. So you will have the zero derivative term, and then you will have the first derivative term. So what the gradient descent does finds the optimal solution of the first order Taylor approximation of the function. And what the Hessian does, it brings the Taylor approximation to a second step. So you have the zero order term, the first order term, and the second order term, and then you find the minimum of the second order approximation of the function. Does it make sense?
Yeah.
So let me ask you something. Here you see an h to the -1, right? So we always say, oh, be careful when you take the h to the -1, because if you have eigenvalues close to 0, if you have eigenvalues close to 0, then you have a numerically unstable setting. Yeah. Did you encounter something like this? Did you verify something like this in your case?
Nope, actually.
Okay. Yeah, because the Hessian is a symmetric matrix, so it is positive defined. So it's all the eigenvalues are in the positive plane. So it's a more stable inversion, matrix inversion that. What can we say? It's a more stable inversion that if you just pick a random matrix of the same size. Go ahead.
Yeah. Okay. Next slide. So now I do two kinds of things. So I did the same Poisson regression using atoms versus using stats models. So do I actually get different results? So I implemented Poisson regression from scratch with Adam and compared it directly to a stats model. So I evaluate both models using log likelihood, deviance AIC, and predictions performance on training a data sets. So this is what I found. The results are extremely consistent. So both approaches coverage to essentially the same coefficients and produce nearly identical predictive performance. So the takeaway maybe is, from a modeling standpoint, both methods reach the same Poisson maximum likelihood solution. However, there are some really small differences. So maybe I think that is because atoms may stop very close to the maximum, but not necessarily exactly at the same numerical points. Yep. So unless we run it really long enough or tune the learning rate to very, 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 very small.
Correct.
Yep. Okay, next.
So what about running times? I think, let me think. Because here you implemented Adam, but you didn't use autograd. So what about running time? I guess that the stats model is a longer running time because it's not specialized. Any comments on the running time?
Running time, actually, they both are not slow.
Yeah, because the problem size is very small as well, right?
Yep.
So of course, if you had hundreds of parameters, then it will be a more noticeable difference. So
yeah.
Okay. So basically, that was my comment, right? So the performance is the same because the problem is small, right? So when the problem starts getting larger and larger, that's when you see more significant differences, of course.
Yeah.
Go ahead.
Okay, so now I'm going to talk about the regressions. So real data sets often contains noisy signals or complete features, and maybe can lead to overfitting or unstable coefficient estimates. So to address this, we do regularization techniques like L1 and L2. So why do we do regularizations? There are two reasons. The first one is to prevent overfitting. So when features are noisy or the model is flexible, regularization helps generalize better to unseen data. And the second one is to improve interpretability and stability. Next.
I will argue that the second point are actually 2 points. So I will argue that there are 3 points, right?
Okay.
Because one is interpretability, one is stability. I think.
Okay.
3 points. Yeah. Like interpretability and stability are not very, not too close in my mind. Anyway, Go ahead.
And now it's L1 versus L2. So L1, which is Lasso, adds a penalty proportion to the absolute value of coefficients, which is the alpha, beta, and this encourages spare models. Some coefficients become exactly 0. So this means automatic feature selection. Now L2 is rigid, adds a penalty proportion to the squared coefficients. This alpha, beta, square roots. Yeah, so it shrinks coefficients smoothly towards 0, but rarely estimates features completely. So this helps when predictors are correlated. So next. So these plots shows how the Poisson regression coefficients change when it increases the regularization strength, alpha, on a log scale. So in the top plots, we see as alpha increases, several coefficients shrinks all the way to 0. So a few features remain non-zero, meaning the model selects them as more informative. So this behavior reflects the nature of Lasso, which encourages sparsity. And as the bottom plot, which is L2, all coefficients shrinks gradually towards 0, and none of them are driven to exactly 0. So the movement is smoother and more continuous than with Lasso. So this is a characteristic of rigid regression. Yep.
Okay. Can you hear me? Okay. In part 5, we use polynomial feature to generate interaction terms and use cross-validation to compare the difference between the basic Poisson and the Poisson model adding interaction feature. Okay, next. The interaction terms Poisson average cross-valid score had improved a little bit on average. Next. The model was trained using different combination of hyperparameters And the best performed was achieved with degree equal 2 and alpha equal 1. It's
Wait,
corresponding.
let me parse this a second. Mean test score, polynomial degree. So here, do you also have all the interaction terms? You also have all the interaction terms, right?
Sorry, I can't understand the problem.
No, I'm just trying to understand this. So when you fix the polynomial degree, right? Do you also allow for all the interaction term up to this polynomial degree? Or this is just, yeah, go ahead.
And I just try different combination of degree and alpha.
Okay, go ahead.
The best cross-validation score is 0.07, I think. Okay, next page. And we also test the feature importance. Next. The first is alcohol. The higher alcohol content generally indicates better wine qualities. And the second one is surface. The surface help prevent oxidation and stabilize the flavor profile of wine. And the third is volatile acidity times total sulfur dioxide. And then it's fixed acidity times pH. Okay, next. In part 6, we use the mixed Poisson model to train the data. And why we have to use the mixed Poisson model is that the standard Poisson model uses the same parameter on all sample. But in reality, the different patch of wine or the different taster will cause difference. And it's called unobserved heterogeneity. So we add the random effect into the model. Okay, next. In this trial, we use negative binomial model to account for over dispersion and assert the random intercepts. The orange points are more concentrated, indicate that the mixed model demonstrates superior predictive performance compared to a simple Poisson model. Next.
But the y here, so the y here, you're printing the score, right? Why does the y go to 140? Can you? Well, here you're predicting the score, right? The range of the score is between 0 and 10. Why does your y go to 140? Am I missing something?
We just say the actual y value.
Yeah, but if you go to the next slide.
Okay.
The next y goes between 0 and 10, right?
In this part, the random intercept difference across group reflect clear between group variability. Let's confirm that including random effect is necessary to capture this group level difference. Okay, next page. The Poisson residual showed a strong vice group, indicate that over dispersion. And the negative binomial model produce residual that are more centralized and symmetric, showing that the model better fits the data and capture existing random intercept across groups. This is the conclusion. The first one is introducing random effect along the model to capture an observed group level, leading to a more accurate and reliable estimate. And the second is the fixed intercept reflect the overall trend, while the random intercept capture the group's specific deviations. Third, the negative binomial model effectively improves prediction accuracy and correct the over-dispersion issue observed in the Poisson model. And then is when group level structure exists in the data set, It is essential to increase model complexity by including randomness. And overall, incorporating random effects significantly mitigate over dispersion and more realistic. Okay.
Okay, very good. Thank you, guys. Thank you, guys. Okay, very good. Any comments? No, I think I think you guys did a good job. I like that you implemented the optimizer by yourselves. Yeah, that was nice. Good. Okay, so now we go to the so notice the guide up with the rules here. Okay, so go on Slack and check this document, right? So these documents are the new leaders that we have. Now, when you click there, you have to present this. So let me go through the groups, and now the leader can tell me. Yeah, just tell me a little bit. Just tell me a little bit how is it going? How is the recruitment going? If you know who you're gonna pick, so on and so on and so on. Just tell me something that will reassure me that you're gonna be ready for presenting the next challenge next week. Okay, very good. Group A, tell me something. Group A.
Hello.
Hello.
You want to know how the progress is going, right?
I mean, so let's do this. So do you know who you want in your group?
I didn't make a group yet or anything, but
did anybody contact you for being in your group?
Not yet, I think. Like,
okay, very good, very good. Okay, go ahead.
What do you mean? Like, I am not sure. Like, I have asked, like, in my current group, if some people wanted to join. I have one people who already had a group, and the other people didn't read my message yet. And like, I'm not sure if they want to join or not. So
you have to fight to get the good people, right? So we are trying to inject some competition in the group recruitment. Okay, very good. Did you read the challenge? How is the challenge going?
I didn't read it yet. I was planning to do it like after this lecture.
I think that's your constant, right? At least this time you noticed that what was written on Slack, right? I think last time you didn't even know that. Just joking,
yes.
Just joking. Okay. So I'll write no progress yet. Okay.
No progress.
But by next week, please.
There will be progress.
There will be progress for sure. I am sure. I have no doubts. Okay. Very good. Group B, tell me something. Leader of Group B. Group B. Group B. So there is. Remember that Group B. There is the
challenges 3.
Yes. Tell me something.
I just recruit members. So now we have 5 members, and one just responds me. So I haven't filled his name to the chart.
Okay. So, but you're gonna have 6 members in total, yeah?
5.
5 members. Okay, very good.
Include me.
So tell me, how did you recruit these members? Was that using your personal charisma? Did you evaluate their capabilities through the previous challenges? How did you find these 5 team members?
Some of them I was in same group with them in other course, so I know their
in other courses.
Very good.
Very good. Okay, go ahead. What about that?
So I message them to ask them, do you want to join my group? And they say yes. Yeah, that's it.
How is it? Do you think you are going to be able to lead the team, the same team, in the next few challenges? Do you think you will? People will come and go. What's your feeling? Are you still evaluating the members? Tell me a little bit. What is your strategy?
At first, I will discuss with them how to separate our work. And after this challenge, because this is the first challenge for this new group, and after that, I will evaluate what they are good at. So maybe someone can exchange their part in other challenge. Yeah.
Very good. Very good. Very good. Okay. Thank you so much. Group C. Group C is the leader of Group C here. is the leader of group C here. Leader of group C. Let's see, are you around? Let me check the chat. Let me check the group C. Group C, who is it? No, I think we don't have him. I think we don't have him. Okay. No show. Okay, group D. Is there somebody from, is the leader from group D here? Group C leader. Group D leader. I think some people took the day out, maybe. Okay. Group E. Is there a group E leader? Is the person here? Wait, we're missing everybody. Group E, no group E. Missing everybody. Okay. Okay. Yeah. No, nobody else. It seems.
I've been selected for the group leader for group F.
Group F.
Yeah.
Okay, go ahead. Then group F.
May I ask that whether I can like give the chance to other people this time in this phase? Because I already said I already been recruited with the group C, and the leader asked me to participate in their team. So I want to ask if there's a chance to give this chance to other people this time in this phase.
Okay, you tell me by next time. Yeah, you tell me by next time, because so after the midterm we have a drop of people that want to focus on some maybe mandatory classes. So we might have a reduction of people. So this week you just stay and listen if somebody looks for you. If more than 3 people want to be in your team, then you shall be a leader again. If you don't get 3 people, then we redistribute among the other classes and you go join group C.
Okay, thank you.
So, but is the leader of group C here? Is in the class?
No, he have some other things to do. I believe this.
Which is taking a break after midterm week, right? That's what she has to do.
But we already kind of discussed about the recruiting for the next challenge. I think he knows he is the leader.
Very good, very good. Okay, so any other leader that wants to talk to me? So group C is like wants to join group C. I told him to see how many look for him. Okay, very good. Yeah, so we can move on, I think, guys, no problem. Any other question about the class organization, about something else? Is there something else we want to discuss? Otherwise, I suggest we take a 5 minutes break and then we move to logistic regression. Is that okay? Any more questions for you guys? Okay, let's take a 5 minutes break then, guys. And then when we come back, we'll discuss about logistic regression. And yeah, let me know on Slack if you want to go running tomorrow, okay? If there are, let's say, 5 or 6 people, we all go running together. And I will get my super fast TA, Sergio, to smoke all you guys. And yeah, it'll be a fun time. Okay, see you later, guys. 5 minutes. Okay, guys, slow restart. I hope you drank some water and you walked around a little bit. So today we do logistic regression, which should be something fun. And just a second. So let me start. View full screen mode. Okay, good. And here we go. Logistic regression. No, wrong share. Wrong share. Wrong share. This one here. Okay, very good. As always, we thank our friends at Harvard, where we very happily steal the slides. So introduction to classification. So now this is going to be a machine learning model for classification. So this is a new problem that you haven't seen before. We're going to argue that classification is substantially different from linear regression, as you should have realized after challenge 2, which is the one that you just did, and challenge 3, which is the one that you should be working on right now. And then we're going to look at the binary response and logistic regression models, and then some motivation and estimation fundamentals connected to this classification problem. Okay, so remember that we have this example, which we always use, which is the sales revenue from a certain split of the advertisement. And notice here that the predictors are continuous variables, and the response is also a continuous variable. In this case, it's a positive variable, and we commented in the last challenge about the role of positive variables. The new challenge also goes into the significance of dealing with positive variables. But then we also have our hard data. Remember that we have the different patients. Patients have different physiological measurements, and we have to predict whether they have a heart disease, right? We're predicting if they are going to come into the emergency room with a heart attack, basically. Okay, so notice here that the response variable is binary, and the other variables, the input variables, are continuous or discrete. Okay, so this data contains a binary outcome of a heart disease for a certain amount of patients that come into the emergency room with chest pain. So if yes indicates that they did come in and had a angiographic test, right, that they confirm that they have some heart condition, and no means they didn't have a heart disease. And we have 13 predictors: age, sex, cholesterol level, max heart rate, and so on. So the idea is what we were discussing before in the presentation of Group B, is that the response variable in this case is what you will call qualitative or categorical or a classification problem, right? So what we're predicting here is a category, and so we are this type of problems in which your model is predicting a different category. It's usually called a classification problem, okay? Because class, category, they're all synonyms. So the idea is that we want to have a model that predicts the category of Y with a response given the input variable X. Okay, very good. So there are many motivating examples. As we discussed before, what you want to sort of stress is that there is, let's say, the label which we attach to a certain class do not really correspond to a certain geometry of the answer. Okay, so for example, the example that we did with the wine, we had scores that were discrete scores, right? So you could say that you have a class 0, class 1, class 2, all the way to class 10, where the number indicates the quality of the wine, and so there was an idea of closeness in the label predicted. So if you predict a label with score of 5 instead of the label instead of the one with score 6, then there was sort of a geometric meaning of the error, right? So if you take 5 minus 6, then this is a different in, let's say, along the same scale. But when we're dealing with categorical variables, right, we could have some of the category of, for example, student or parent or grandfather. Remember this type of example that we had before. So you cannot really establish a geometry between the different classes. You cannot say that a father is this much unit away from a son, something of the sort. Okay. So the first question is, why don't we use linear regression? And this is what we are arguing now, right? So remember that we had another data set in which we have x being some of the I don't remember what is the axis. X are some of the feature of people, and Y is the department that they belong to. And here we have three possible answers: computer science, statistics, and otherwise. And again, this is a case in which we have three categories, three classes. And of course, we cannot establish a geometry between the answers, right? You cannot say that a computer scientist is closer to a statistician than somebody that does economics, right? So it doesn't make sense to establish an error, right, in the prediction, which depends on the idea of distances among the classes. So we have to deal with this. Okay, we have to deal with the fact that the error that we commit cannot be quantified in terms of distance between the true label and the predicted label. Okay, so let's focus on a simple case in which we only have two classes. So then now the classification problem that we're dealing with is simply a binary classification problem. Binary meaning two, so that we only have two classes. We have to break 0 or 1. So a first approach that we could have, given that now the geometry of the problem is simplified to only two labels, is that we could use a linear predictor, and then we threshold the answers. Some of you did this also in challenge 2. So when you implemented the linear regressor, then you just thresholded the value to the closest integer, so that then the predicted value will still be in the restricted support. Of course, if we only have two classes, then this presents fewer problems than if we had 10 classes, so that we will have to decide an ordering of the classes. In this case, we only have two classes, so there is no ordering of sort. So the type of model that we are implementing here will be something like this. For simplicity, right, we just have a max heart rate, and we do a linear regression over the points that are in the data set, and we see how many are heart rate, how many have a heart disease, how many don't have a heart disease. Of course, here you are simplifying the model to have only one input variable for the visualization purposes. But the idea is that we could do, at least what we could do is that we could go back and reinterpret the prediction of the linear regressor to be the probability that a certain person has a heart disease. And then when we do the thresholding, we take a hard decision based on the probability that we observe from the linear regression model. And we could say, of course, if the probability goes between is above 0.5, then it is feasible to say that the person has a heart disease from the prediction of the model. Okay, this seems to be a reasonable approach, right? Because let's say it retains a sort of interpretation of the prediction in terms of probability. So we like this because it's sort of indicating us a sort of confidence of the decision that we are taking. But we clearly run into a problem because of course, the linear regression could predict above 1 and below 0. Okay, so we have a certain problem with the extreme classes. What happens if the prediction is -1? How are we going to map it in form of probability? What happens if it's above 1? How do we predict this in probability? But the more substantial issue is the one of substance, meaning that if we look at a certain heart rate, right, what we observe is a percentage of people at that heart rate that had the heart disease and a percentage of people that didn't have the heart disease for that heart rate. So the model should try to capture the proportion of the label, right, that have the same input feature. Okay, so here you can imagine that you can fix the input feature. When you fix the input feature, you go through the data set and you pick out all the elements that have the same set of input features. And what you're going to obtain there is a subset of the data set where you're going to have a certain proportion of inputs that correspond to a heart disease and a certain percentage of the input that corresponds to no heart disease. And this is substantially different from what the linear regression model does, right? Because the linear regression model is simply trying to pass through all the points that are present in the data set. And this is not what we should be doing here. What we should be doing here will be to predict the percentage of labels at a certain input features that present 0 versus the percentage that presents a 1, okay? So it is a substantially different problem that we are facing. Okay, good. So now we know what is the job, right? We want to have a linear regression model. We want to have a machine learning model that predicts this proportion of heart disease versus no heart disease that we're going to sort of reinterpret as a probability, right? Because if you have 100 individuals and the probability that you have a heart rate disease is 13%, then you expect that out of the 100 people, 13 will have heart disease and the other 87 does not have it. Okay, so so we want to have a model that does more on the left, more behaves more like the function on the right than on the function on the left. Okay, so in the left we see that there was a gradual increase, let's say, of the predicted heart disease as a function of the feature X, and this is not desirable. What we would like to have is more of a behavior on the right, in which we have the sort of a region of almost certainty that the heart disease is not present, a region of almost certainty in which the heart disease is present, and we predict a fraction, right, of people having a heart disease for only a subset of the input features. Okay, this is again the cognitive bias, right? So from our understanding of the data that we observe, we will expect that this is a desirable behavior of the function that we are going to implement. Good. Okay, so we can focus on this type of model. Okay, so we could take a sigmoid to be the function that we're trying to determine, and we parameterize the sigmoid by this beta 0 and beta 1. So we say we have a term which is the input to the sigmoid, which is e to the b0 plus b1x. So this, let's call this m. Okay, so this we're going to generate a probability from the m as m over 1 plus m. We're going to see later what is the meaning of the m here, and then we're going to say that for our m we want an exponential dependency from the betas, and so that we sort of put a linear regressor in the exponent of the m that then goes in the sigmoid. Okay, good. So of course you understand how this x can be an input vector, right? So that then this is a scalar which takes in input. It's a function that produces a scalar and takes in input a vector x. And what we want to do when we train the machine learning model is that we want to find the vector of betas, right? So the b1, the b0 plus the b1 plus whatever all the other b's that we have, and we want to find these values so that something is minimized. And this something is something that we still have to comment, which is how are we going to evaluate the prediction of the model versus the actual levels. Okay, let's move forward slowly. So once we have trained the model, which we still don't know how to do it, okay, but what we're going to have will be an S-shaped curve, and this curve is going to be a logistic function. And the way in which you can interpret the b0 and the b1 in the scalar case, right, in the two-parameter case, is as follows, right? So the b0 plus b1 controls how far away you are from the crossing the 0. Okay, so you can imagine that you have this S function and you have a transition between 0 and 1, and what you can control is the slope of the transition and the x-axis in which the transition happens. So the point on the x-axis in which the transition happens is related roughly, of course, to the minus b0 plus b1 value, and the slope is b1 over 4. Okay, So that then if you do a linear approximation of the slope, you will get that the slope goes from 0 to 1 in this with linear, right, with the slope of the linear function, which is 2 over b1. Okay? So this is something that you have to remember. This will provide the interpretation of the b0 plus b1. Of course, it's not as intuitive as it was for the linear regression, and it's not as intuitive as it was for the Poisson scenario that you saw in the previous challenge, but that's how we live. That's we try to gain as much as possible from the model that we choose to train for solving a certain problem. If the interpretability is hindered or can only be gained after working with the model for a long time, that's the life that we've chosen for ourselves. And this is where this slide is where we comment further on the choice of the sigma that we have. So when you take the first statistic course, the first few slides in the course should contain the history of statistics. And when they do the history of statistics, they tell you, oh, when we teach statistics today, we have the 3 axioms of statistics. But before we landed on this formulation, there was a previous attempt of describing a theory of random events, and that dealt with odds. So when you deal with odds, then you can also build sort of a system of prediction of random events. It doesn't work like probabilities, but how do people define odds? This plot explains to you the difference between odds and probability, right? So imagine that you have a ball with 10. You have a ball with 10 balls inside. You have 4 blue balls and 7 yellow balls. You can define what you predict when you randomly pick a ball from the from the urn. Let's say urn, otherwise ball and ball and ball. I'm going to confuse myself. You can say you can have a different description, right, of the event of drawing a ball from the urn, and you could say, well, if I draw a ball, am I going to observe a blue or a yellow one? You can describe the odd of picking a blue and the probability of picking a blue. Okay, so the odd of picking the blue will be the number of blue divided by the number of yellow. Okay, so you see how many times you draw the blue, and you say, well, I have 4 over 7. My odds of drawing a blue versus a red are 4 over 7. Or you can say the probability that I pick a blue is 4 over 10. Okay, it's a subtle difference, but yeah, as I said, in the history of statistics, we tried both, and we liked the probability more. There were some smarter people probably that worked on this problem, so we landed on this. But the mapping between probability and odds, given an event, is the formula on top. So the odd of a certain event A is the probability of A divided by 1 minus the probability of A. And so the interpretation of the log regression that we have is that the model is predicting the odds of the outcome being 1. Okay, so if you go back to the formula that we had in the slides before, this beautiful formula here, right? You can take the log of this object, and the log of this object will be the log of the odds. So this is sometimes a term that people use. You say that the parameter beta controls the log odds given an input x. So you're given an input x, you multiply it by your model parameter betas, and you obtain the log odds. Okay, good. So this is again an interpretation as of why we have this formulation where we take a sigmoid, and then we put in an exponent, and add the exponent of this term, we put a linear regression term, basically, right? We get a linear mixing between the beta and the x. Okay, so now we have an interpretation of this beta as follows, right? So the natural interpretation is as follows: the unit of change in x is associated with beta 1 change in the log odds of success. So here the x increase of 1. We're going to have an increase of b1 in the log odds. And so the unit of change of s is associated with e to the b1 multiplicative change in the odds of success. Okay, so this is the same as the Poisson case, right? So the B1 parameter controls the multiplicative factor of change with the term e to the B1. So you should have seen this in the previous challenge. Good. Okay, so we are halfway there. So we say which model we choose, and we say which where the betas go inside this model, and then we are describing what is the interpretation of these beta parameters. Of course, this works well when you have a few parameters, and so the intuition is a little bit clearer. Now the question is that if we had to connect this to an estimation problem, right? What type of estimation would will this be? And answering this question will tell us how we're going to compute the loss for the logistic regression model. Okay. So unlike in the linear regression where there exists a closed form solution finding the estimate beta 0 for the two parameters, the logistic regression estimate cannot be calculated through a simple matrix multiplication. This is what we said multiple times, that the linear regression is a blessing to us because it has a closed form interpretation, which is very helpful for us to build the intuition of the solution we get. But in general, forget about closed form solution. These are a gift that you don't receive often. So next, the question that remain for us are what type of loss function should we use, given, as we said, that there is no geometric interpretation of an error that you do in a categorical prediction. Then we want to know what is the probabilistic perspective that we have, as we did in logistic regression, and sort of we expect to see a log likelihood function, and the log likelihood function is going to provide us a Bayesian interpretation of the model that we've chosen and the loss that we've chosen. Very good. So remember what is the PMF that we were dealing with. In a sense, we want a model that predicts the probability that we observe a 1 versus the probability that we observe a 0. So this probability, let's call it P. So what we are predicting is a single parameter, which is the P and the 1 minus P. And if we want to simplify this, if we want to write in a mathematically elegant way, we can just say that the probability that y is equal to small y is equal to P to the y, 1 minus P, 1 minus y. Very simple, meaning that the y takes value either 0 or 1. If your p is equal to 1, your 1 minus p is equal to 0. So only the first two terms of the equation make sense. So you have that your p is equal to 1 is equal to p. And if your p is equal to 0, if your p is equal to 1, if your p is equal to 0, then only the second part of the equation is active, and you get the value 1 minus p. Very easy. So this middle formula here is just for you guys to compactly write the first two equations as a function of p, knowing that the y can take value either 0 or 1. Okay, then we say, well, the probability that p is equal to 1 given that x is equal to small x is equal to 1 over 1 plus e to the minus v0 plus v1 times x. And this is what we said before. The way where we want to put our parameter vector is in the exponent. So then when we go back and look at the probability, we obtain this term. So remember that we obtain this term also here. Good. See, this is where we take the form. So we have chosen to control the probability of y being equal to 1 given x is equal to x with this nice form. Very good. And the idea is that if somebody gives you the same input vector x, then the estimate is deterministically always the same. Right? So this is a deterministic mapping between the input features and the prediction. And remember that we're going to interpret this as a ratio, right? So when we fix the label y, we're going to have a lot of data set. When we fix the label x to be equal to small x, we're going to have a large number of observations that for the same input x, either take value 1 or take value 0. And we're going to predict that the ratio of zeros versus the ratio of 1 is going to be controlled by this relationship, okay, by this model. Very good. So now we have determined that we are predicting the probability of this y equal to yi being equal to small yi. So the label is going to influence this way. As usual, we say, well, if we have a data set of yi observation, then the probability that my model is predicting is the product of the prediction for all of the entry in the data set. As we did before in the previous challenge, we don't like to have multiplications. They are numerically unstable, and we don't want to deal with them. So we just take the log. When we take the log, the probability becomes a summation. The product becomes a summation. So now we get to the summation over the I, yi log of pi, 1 minus yi log of 1 minus pi. Very good. Okay, so if somebody gives us a beta, we can try to see what the probabilities are predicted by the beta, and we can try to see what is the difference between the proportion of zeros and one for a certain input feature in the true data set versus the predicted data set, versus the prediction. Okay. So in this loss function, right, you see that the ratio is controlled by the pi, and here in the ratio we put in our odds as we saw them before. So now we have the L, the log likelihood function of p given y, being equal to this elements. For the input yi, I would have predicted a portion pi. The portion of pi will be controlled by this guy, and so on and so forth. Okay. So when you sum over the data set here, you have all the times that you observe a certain yi for a certain xi. And when you take this summation, then you will see that the proportion, right, the ni in which the yi was equal to 1 will appear here. This will be n minus ni. And so this function is really a loss function. Okay, it's really measuring the distance between the proportion of zeros and one for a certain input x that was predicted by the model versus the true ratio of zeros and ones that you observe in your dataset. Okay, very good. It looks messy, but we know that we have to move forward, right? In order to move forward, what do we have to do? We have to find the derivative of this object with respect to the unknown parameter beta, and then we want to find the minimum of the function given the function beta. Good. So this looks a little bit messy, right? So when you take the derivative of this object, it's not going to look nice. The equation is not going to fit on the page, so we're not too particularly happy. But in a sense, in this course, we don't deal with necessarily with the problem of the optimization problem. So we're just going to say that we give this to somebody else that can do optimization better than what we can, or better than what we have discussed so far in the class. And then we go and see what is the minimum of this loss function when we take the derivative and set the derivative to 0 to find the best betas. Okay, good. So then we do this. Somebody gives us a model. And so when we plot the prediction of the model over all the possible input features, we're going to observe this S-curve. And this S-curve is going to, again, predict the proportion of zeros and one for a certain input. Yeah. So here, just intuitively, right? So what you observe here is that this is the region in which your model predict almost zero probability of heart disease. And you see that here, when you plot the data set, you don't have any zeros. And here, this is the region in which you don't have the heart disease, and you see here that there are no ones. So in a sense, you have this S function, and the S function has to go all the way to very close to 1 and all the way very close to 0 at the two edges. Of course, these two regions can be flipped, right? So the shape of the S can be the true S or the flipped S, whatever it is, depending on the relationship of the data. And then we have this transition in the middle. And you see here that in this specific case, we have a very large transition, meaning that the saturation of the sigmoid doesn't occur in the ranges of, it doesn't occur for, let's say, the intermediate ranges of the maximum height. Good. Of course, we are working in Python, so we don't care for any of the optimization details at the moment. What you do is that you call up your logistic regression model from your sklearn. You put in some the right parameters. You tell the Python if your data is scaled or not scaled, and then you can obtain the coefficients beta 0 and beta 1. In this case, the probability. In this case, the problem is linear, so we only have two coefficients, and you get these two numbers, and then you go back to your interpretation as e to the b factor or multiplied factor of increase, and you know what to do. Good. Once you have this model, what you can say is you can answer the following questions. So you can write down the model, right? So you can explicitly write the relationship between input and output. You can interpret the B1 and the B0 in terms of this crossing and slope, and you can estimate the probability that somebody has a heart disease if they have a max rate approximately equal to 2,000. And this is the value of your logistic regression model. Okay. So let's go back to the case in which the input variable are continuous or discrete. So remember that we discussed this before. We said, well, if you have a qualitative variable, you can add an indicator function, and then you can train the model for this indicator function. And in the linear regression case, this will give you a model with a different slope depending on this variable. So it's as if you specialize the model into two submodels controlled by this indicator function. And this is the same here, right? So let's say that in the X we have a binary data. Then you see there is as if you have two different sub-predictors, right? With two different values of B0 and B1, which are controlled by the binary variable. Okay. And remember that, so you can solve the estimate mathematically in closed form. And the other question that we want to always answer is what is the likelihood, what is the reliability that we have in our estimates. So now we know how to do this, right? So we will do some bootstrapping, some cross-validation, so that we can get a distribution of the B0 and the B1 over the different cross-validation folds, and we can have a distribution of the coefficients, so we can see how high the estimate of this parameter is. Just remember that the uncertainty over these coefficients in logistic regression, it's qualitatively different than in linear regression, because here you have a multiplicative factor, right? So this multiplicative uncertainty, you can understand how it plays a role, right? So for small values of beta, you prefer a multiplicative uncertainty to an additive uncertainty, right? Because if the influence is small, then a factor 2 multiplied by a small number is still a factor 2. But as the betas grow large, then the linear uncertainty is much better than the multiplicative uncertainty, because of course 10 times 10 is equal to 100, but 10 plus 10 is equal to 20, right? So the multiplicative uncertainty hits you when the value of the coefficients beta is large. So you look at the magnitude of the coefficients beta, and sort in your mind you have to adjust for the sensitivity of the model to this multiplicative uncertainty. Okay. So when you run it on Python, you have the usual interpretation. You have LLR values, you have covariance, and so on and so forth. So we don't need to discuss it. This is the usual stuff. And yeah, so this is the first part of the presentation. Let me stop a second and see if there is any question. Any questions? Otherwise, we go to the part 2. You guys know that frontal teaching is not my favorite things in the world. I'd rather listen to you than do any frontal teaching. Okay. So no questions so far. Okay. I see that you guys are trying to organize the teams while you're doing class, which I don't. Yeah. It's not a problem. You can always go back and look at the class on YouTube. Remember to drop a like and subscribe to the channel, so I can move toward the monetization of my YouTube channel, which I think is coming any decade soon. You know, in the next few decades, I'm sure I'm going to reach monetization and make some money from my YouTube videos. Very good. So since we already did the linear regression, we know what's coming next, right? So we can add interaction coefficients. And we can add some regularization, and then we can try to visualize the region in which the model does a certain prediction. So this is new for us. Okay, good. So as we said, if somebody gives you data, you always have the issue that you have to decide if the complexity of the model is sufficient, right, to meet the complexity of the process that generated the data. And what you can do is always you can try to make your model more complicated by artificially generating more input data. And the way you do this in this class is to consider polynomial and product of terms. And so you can, so you know how to do this from the linear regression, right? And the question always appears, it's like, oh, if you obtain an interaction term, how can we interpret the interaction terms? In the linear regression case, we had a better understanding for this happens. Now everything goes to this exponential, so we have this multiplicative conversion of the influence terms. So you have to gain some understanding of this relationship, because for us human it's difficult to operate on the exponential scale, on the logarithmic scale. But what can we do? And now we can move to classification boundaries, meaning that what the model prediction is still a number between 0 and 1. Okay, and the number between 0 and 1 now it's interpreted as a proportion of the data that for a certain input label will have a feature, an output label equal to 0 equal to 1. So what you can do is that you could say, well, let's just see, right, at which value of our input feature x, right, I'm going to move between a number below 0.5 to a number above 0.5. Okay, so this is a very natural thing to do. So what you're doing is that you're solving an equation, right? You're saying, well, py equal to 1 is equal to 0.5. You go back to your equation. You know that your log odds have to be equal to this. So 0.5 is equal to 1. Log of 1 is equal to 0. So you're looking for this equation, okay? So you're looking for the b times x, of course, in vector form, to be equal to 0. I know that you guys love linear algebra as much as I do, and you recognize this as the equation of a plane. So you want to look for the plane, right, in the space X, in which the decision boundary lives, right, where you switch from a probability below 0.5 to a probability above 0.5. This corresponds to the fact that if you had to make a hard decision, so output a 0 or a 1 from your model, you will discretize the output of the logistic regression model, and the way you do the discretization usually will be with a 0.5 threshold. Good. So here we repeat the experiment with this heart rate data set. We train the model over these two features. Of course, the issue is that we pick two features so that we can see a classification boundary, which is a line, and divides the plane into two half planes. Okay, so this is as follows, right? So what we're doing here is that we are plotting this equation, this decision boundary. Noting that this decision boundary it's over two parameters. So what you can do then is that you go back to your data set and you plot for the same two parameters, the zeros and the ones that you had. And now you have an interpretable scatter plot of what your model is doing, right? Your model is saying that the halfway prediction, right, the 0.5 prediction, lives on a hyperplane, and the points that are below the hyperplane receive the 0 label, and the one above they receive a 1 label. Okay, so this is how you represent it, and you can see very well that now we have this sort of separating hyperplane between the 0 label and the 1 label. Okay, so we haven't defined distance between points and hyperplanes yet, but you understand what it's trying to do, right? So we're trying to keep the proportion of the 0 label and the 1 label as separated as possible through this line, and then you will do the prediction based on this decision boundary. So even if the interpretation through the proportion this sort of gives a softness to the model, right? It gives a smoothness to the prediction, a reliability aspect to the prediction. You can always go back to the hard decision and have a much more, let's say, intuitive and sharp interpretation of the result of the model. Good. So you can do this in. So what is happening here? I think it's you guys can guess it, right? So in this case, we have two different variables, right? So we're still in dimension 2, and we want to have a decision boundary. But of course, if we limit ourselves to, let's say, linear terms inside the exponential in the sigmoid, then we can only have hyperplanes. This makes us very unhappy because we, of course, the idea that these labels are linearly separable, it's very optimistic. So what we can do is that we can add some interaction terms. Of course, if you go to a polynomial of degree 2, then with these interaction terms and the polynomial degree terms for the input, then you can describe a circle. And this is telling you that if you go up with the complexity of the model and you add polynomial terms, then you could describe decision boundaries which are elliptical. And so you can capture, let's say, a more complex geometrical shape in the higher dimension. Good. Regularization as always, right? So so when we talk about these interaction terms, then we have the issue that the model complexity grows very large. So we want to add some regularization, as we said before, in order to add what did the student say? Interpretability, of course. What did you say? Robustness. And what was the three things that he said? Group B, remind me. Interpretability, scalability, and simplicity, right? So in this case, we could use a linear predictor in this case, right? Because we have a very clear separation between the zeros and the ones. And if this model, right, can be separated exactly in 0.1, then this means that there are multiple linear regression models that will be able to separate this, okay? And you understand that if we have multiple models that can do the same job, this seems to be a good thing at the beginning, but then of course you know that this is going to cause errors in your optimizer, because your optimizer is going to get to a certain point and then there's going to be a zero gradient all around it, right? So if you're in a certain model and you move in the surrounding of the certain model, the gradient is always zero because you're always separating things exactly, and so this will cause numerical instability. Of course, this is the simple case in which this happens in the scalar case, in one input and one output. If you go into higher dimension, then it's not nice to have zero gradients in some of the dimension or maybe in some of the directions. And so this will create instability in your optimizer. Good. So if you run your linear regression scale-learned model, it will tell you that there is a perfect separation error, meaning that over some of the dimensions, you obtain perfect separation. So when you take the derivative of the model, you go to zero because in every direction, you will still obtain perfect separation. So the gradient is always zero. Okay, not nice. So what you want to do in this case is that you want to add some regularization. And if you add some regularization, this is going to prevent your gradient from going to zero. And what you can do is, as usual, you can put a ridge regression. And the ridge regression is going to do the sort of it's going to have an automatic magnitude of control of the coefficients. It is always nice to have the smaller coefficients because it means that generally inputs have lower influence on the prediction. So smaller coefficients mean that the prediction is more stable, more robust. And so this nice regularization terms is going to shrink the coefficient towards zero, which means also that it's going to make the gradient non-zero. And among all the models that are able to do the perfect separation, your optimizer is going to go toward the model with the smallest parameters. And this model, of course, it's more robust, more interpretable. Of course, we will prefer L1 regularization so that we know that they will be pushed to zero instead of being pushed to be very small. But we already learned this lesson in our linear regression model. Okay. Good. And now we can do the following. So we can add an L2 regularization, and then we can do the plot that you guys also had in your plot. So here you have the C, right? The C works as a penalty. And what you have here is that you plot, let me just check, so I have to remember. We plot the beta 1, 1 and the beta 1, 2. One is with the red and one with the blue. And the lesson that we are learning here is that the C penalty, right? As the C penalty, just a second. Exactly. So one is the L1 regularization, the other one is the L2 regularization. The L1 is the red one, and the L2 is the blue one. Okay, good. Okay, so we see this. You observe this also in your Poisson experiment before, and this is what happens, right? That if you choose an L2 regularization, you are with a much smoother trajectory, you goes to 0. If you choose L1, you know there is going to be a value of the penalty for which you switch to 0. But this might come at the cost of a jump. We already commented on this in the last lecture, right? So you don't want to see jump in amplitude, especially relative amplitude of the coefficients, because it means that if you move your regularization a little bit, then the model will switch the relative importance of the features. And you don't want to see this switch happens, because this affects your interpretability. It makes you panic that you have some collinearity, for example. And so you prefer, you like the automatic control of the L1 regularization, but of course you don't want to see this rapid jump in the trajectory, in the amplitude of the coefficients, and this is what you observe in this curve, in this slide. So very good. So you have to choose the shrinkage factor. As usually, there is no fixed rule. You have to sacrifice some of the data to do some hyperparameter tuning, or you have to gain enough experience in the problem. You know how to pick it. Okay, so once you add regularization, right? This also affects your decision boundary. Here we see a very nice example. So first, you have the straight-line model. The straight-line model, what it adds, it has a linear separation between the label zeros and the label ones. So this is very nice, but of course, we are sacrificing something. We are not exactly matching the data. So what we do is that we do a poly 10, right? So we go up to polynomial 10 and we allow for interaction term. And what we gain is that now we have a decision boundary that really follows the shape of the data, but we are overfitting. As we said, the more parameter we have, the more is the likelihood that we're going to overfit. And so what you want to do is that you want to add a regularization term. The regularization term is going to, let's say, send some of the coefficient to 0, or shrink some of the coefficients, so that your model is not overfitting. You are preventing overfitting. Okay, very good. Now, so far, we try to stay away from probability theory, because this is a lab class. It's not a class on probability and data science, or probability and machine learning. But let me just give you some hints of what will be the interpretation of the statistician to this model. I also have a master in statistics, so I'm not pretending to be a statistician. I'm also a statistician on paper. But I'm also an engineer on paper, so I guess that doesn't mean much. So the idea is as follows. What we're dealing with now is the probability of the response variable b is 0 and 1 given the input. So this given, we interpret it as a Bayes rule. So you should have seen Bayes rule a few times in your life by now. So what we have is that the P of A given B, which we interpret of B and A divided by P of B, meaning that we see intuitively, right? We see how many times the event A and the event B occurred at the same time, and we divide by the number of times the event A happens, and this is how we interpret it, again, in terms of probability, in terms of intuition, right? So of all the times that I saw A and B happens, how many times did the probability of A happens, okay? So then this is our beloved Bayes theorem, right? So the P of A, we rewrite it as P of A given B multiplied by P of B, and P of A and B complement by P of B complement. So again, this is just rewriting the equation by noticing, yeah, just nice simple linear algebra. Okay. Good. So now we think about this label in terms, for example, of a result of a diagnosis, right? As we did in the heart rate example, you say, well, there is a certain probability of having the disease, a certain probability of not having the disease. How are we going to deal with this? We're going to do a test, and then we want to know if the test output is positive, what is the probability that you have a disease? We can do a study, right? As you guys all remember from the COVID times, to say, well, every time the test was positive, how many times did I have the disease? How many times did I have the disease when the test was negative? And so on and so forth. So we go toward this matrix that you guys have seen a few times of the F1 score of and false positive and false negative. And you have this beautiful equation, which is as follows. Let's say that we use Bayes' theorem to say, well, the probability that you had the disease, given that the test was positive. Okay, so this is equal to the probability of that you had the disease, that the test was positive and you have the disease, multiplied by the probability of having the disease, divided by the probability of the test being positive, you having the disease, multiplied by the total rate of disease, plus the probability of the test being positive, you not having the disease, minus the probability of the, multiplied by the probability that you don't have the disease. Good. Now, we need to give names to all of these quantities so that we can use the English language to describe what is happening in real life, because communicating in equations is not very common outside engineering. So we call sensitivity, okay, the probability of the test being positive given the disease is present. Again, some specific use of the English language, right? So sensitivity is saying, well, how sensitive is the test of the presence of the disease? If I have the disease, how sensitive is my test? Will be the times that the test was positive, even that you had the disease. Then you have the specificity, which is sort of the opposite, which is how many times the following happens: the test was negative and I didn't have the disease. Okay, good. Prevalence is the probability of having the disease. Positive predictive values is probability of disease being present, given that the test is present. And the other one is the negative predictive values, probability of the disease not being present, given that the test is not present. I always get confused. I forget the meaning of these terms. I was not living in. I never practiced medicine, so I never used these terms as extensively as other people did. But the point is that understanding the interaction between these terms is not trivial, and we always come up with new ways of trying to convey the value of these quantities. Okay, so imagine this: when a disease is not very prevalent, then the number of false positives will overwhelm the number of true positives. Okay. So if you have a very rare disease and you do a test, whatever the test is, let's say, then it's very likely that you're going to have more positive tests than what the true disease is, because the disease is very rare. For example, take the prostate cancer screening. Okay, this has a sensitivity of 90%. Let me go back. Sensitivity. No, test is positive, you have the disease. And the specificity is about 97%. We go back, means that the test is negative when you don't have the disease. Is that? But what is the issue? Is that the prevalence is about 0.1%. So prevalence, probability of the disease being present. So what does that mean? We want to understand what is the positive predictive probability for this diagnostic test. Good. So why do we care about this? So far we were working about labels and zeros and one, and the loss was with respect to the correct prediction or wrong prediction. Why do we care about this? Because you can think about classification as a diagnostic test. Okay, so let yi be equal to k in the event that the observation truly belongs to the category k. Then y hat of k is the event that the predictor correctly say that the entry belongs to that category. then the base rule states that the positive predictive value of the classification is this formula here. Okay, so the probability of a predicted outcome truly being a specific group depends on the proportion, on what, on all the terms that we saw before, and again returns us to the proportion of observation indexes. Good. So there are two major types of error in the classification problem. Now we go back more to the statistics, which is false positive, which is incorrectly predicting y equal to 1 when you have y equal to 0. And you have the false negative, which is incorrectly predicting y hat equal to 0 when the true label is y hat equal to 1. So the result of the classification is described on confusion matrix, which you guys already discovered through the use of ChatGPT. And sometimes people call it a contingency table, which is a 2x2 matrix. And sometimes you also do this beautiful ROC curve. Okay, so this is the confusion matrix. Heart rate being present, heart rate not being present, predicted heart rate, not predicted heart rate. What you want to see is that you want to see a strong diagonal. Okay, so this tells you the positive predicted values and negative predicted values. And then on the off diagonal, you can see there is a particular skew of the test toward misclassification in one of the two directions. Good. Now, the tricky part to understand, right, is that we can drive the entries of this table. Because what we said before is that, well, when we look at the decision region, we fix the decision region to have precision 0.5. And when we say that, we are doing something implicitly. We are saying that for us, predicting a 0 instead of a 1 has the same value of predicting a 1 versus a 0. Okay, so we are saying that an error in one of these two directions is equally damning to us. But of course, in reality, this is not the case. When we think about this test, you can again go back and imagine, right, that you do not want this value to be balanced, right? You don't see the positive predicted value and the negative predicted value in the same way. Why do I say that? If you go to the doctor, right, and the doctor tells you, well, how do you want these values to be balanced? Of course, you are much happy when the first happens. That is, you go to the doctor tells you you have prostate cancer. Then you go and you do more tests, and the tests clarify that you do not have prostate cancer. Okay, so because what is the alternative? The alternative is that you go to the doctor tells you, well, you don't have prostate cancer, but in reality you do have prostate cancer. In that case, you're dead because you do more tests. You don't do the extra test, and since you don't do the extra test, then you end up having a very bad experience, let's say. Maybe I should have taken something less dramatic than cancer, but as always, I'm not very good at choosing these things. But you understand what I mean. Let's take sunny day versus rainy day, okay? So you're much happier if the prediction skews toward the negative outcome, because this has a follow-up in which you might discover that the outcome is actually positive, but you don't want to give a positive outcome when actually the true outcome is negative, okay? So how can we do this? How can we manipulate our prediction so that we skew the prediction toward the rainy day? Okay, because if we skew the prediction toward the rainy day, then people wake up and there is a sunny day, and they are not unhappy with our weather prediction website, which is much better than then planning to go out for a sunny day and then it's actually raining. Let's stay away from cancer. Let's focus on weather prediction. Okay, so what we can do is that we can actually manipulate the threshold over which we predict a 1 versus a 0. Let's call this number pi, and we move the threshold pi toward the higher level so that we predict the ones much more likely. Okay, good. So you see here, right, that if we manipulate the pi to be 0.4 versus 0.6, then this affects the positive rate, right? The positive and negative rate. So if we choose the 0.4, means that we are predicting much more the ones, right? And when actually the true value is 0, and we are doing much less this of predicting the 0 when actually we have the 1. And the other way around, we have the opposite, of course. We are much more likely to predict 0 when actually there was a 1. And of course, given the choice, we decide to do this on our website instead of the latter, because predicting a negative outcome when actually you have a positive outcome is generally considered better than the opposite. In most scenarios, it's better. Okay, so now we come to our beloved ROC, which again, some of you already discovered through the challenges. And ChatGPT explained to you what this is, as we said in the previous lessons. So what happens, the name of this comes from the old World War II era, right, in which I think radar, it was radar operators, right, and people, they were they're trying to describe the detection probabilities there. So the curve illustrates all the possible trade-offs between false and negative positive rate when as a threshold is chosen. Okay, the vertical axis displays the positive predictive value, and the horizontal axis depicts the true negative value. Boom. Here we are. False positive rate, true positive rate, and this is called the ROC. As we said already, the straight line corresponds to a random prediction. Okay, so the straight line means that you randomly predict. If you randomly predict, as you change the threshold, you will predict either always 0 or always 1, and this will draw a line in the middle as you change the rate of prediction of zeros and ones. So this is here. Then what you want to do is that you want to push the prediction toward this angle. Why? Because the ideal test will have a 0 false positive rate and a 1 true positive rate. So your test will never tell you that you have a 0 if you have a 1. And it will always tell you that you have a 1 if the label is a 1. Okay? And so how you move between the totally random and the perfect classifier, right, changes the area under the curve. Here the area is 0.1/2. Here the area of the curve is 1. So not wanting to describe the full curve, what you can say is just what is the amount of area under the curve. And again, you go back to a single scalar, which is easy to communicate and it's easy to mentally deal with in order to describe this more complex scenario, right? So you would say, well, if I just look at the area, I know when the area is good and when the area is bad. Okay, so this measure is AUC, area under the curve. So the larger AUC is better, and it's generally always a good measure for predicting for describing the performance of different models, right? Logistic regression, KNN, decision trees, no problem there. Okay, very good, guys. I think this is it for today. I think this is all I want to cover for today. Let me know if you have other questions. Otherwise, I stop the recording and then you can ask me something else. Okay. Good. Any questions? I'll give you 30 seconds. If not, I'll stop the recording. Say hi to the people on YouTube. They're going to go and subscribe, press like, and I don't know, whatever else they do. And then I'll see you guys next week. Okay? Ciao, ciao.